In this video, I'm going to work through a problem posed in the book Clojure for the Brave and True. This book can be found online for free and is a great resource for learning Clojure. Everything will be written in Clojure. This video isn't about trotting out the basics of Clojure. It is more about demonstrating my thought processes as I work through the specific problem from start to finish. The hope is, along the way, you'll pick up some basics. Each of the Clojure features we'll use can be a rabbit hole leading all the way through Java and into the JVM. We'll try to stay clear of those. So, what's the problem? You'll be given a list of asymmetrical Hobbit body parts, and the first thing we'll need to do is to make the list a symmetrical list. So, for every provided left body part, you'll provide a corresponding right body part, but not all parts have a left and a right side. Secondly, with the symmetrical list of body parts, you'll have to choose one of the body parts at random, taking into account the relative size of each body part. So, for example, the head has a size of 3, whereas the left eye has a size of 1. This means that the head should be 3 times more likely to be chosen than the left eye. That's all we're given. I've already created a new Clojure file called the Hobbit and specified a namespace for the file. But before we get started, I should mention the REPL. It stands for read eval print loop, and it's basically an interactive development environment. It lets you execute arbitrary expressions and see the result printed immediately. So, for example, I can add 1 plus 2, and you'll see the result is 3. I think better than me trying to continue by explaining it in words, it'll be best if you just see it in action, and we'll make extensive use of it while we work through the problem. So what I typed into the REPL is a Clojure expression, and like all expressions in Clojure, it is a list, and a list is marked by parentheses, and it is just a list of elements basically, but for an expression, at least ones that are lists, the first element is important because it has to be something that's invocable, some kind of operation. So in this case it was the add operation. All the elements that follow the first element are basically arguments passed to that initial operation. Now the REPL isn't the only place where we can place expressions. We can also place them in a file. And so if you look at the file and what we have started, we have 2 expressions here. The first one is the namespace, and the second one is this special form of def. And so I'll just fire over with a shortcut the namespace into the REPL, and then I'll send over into the context of the REPL So now within the REPL, this symbol, which is bound to this vector, is available for us in the REPL. So one of the ways we can test that is we can just say, look, evaluate this symbol, and you can see that we just get the value back. The value is a vector. We know that by the fact that it has square brackets. The elements in this vector are a map. The map you can see as curly braces, and it is composed of key value pairs. And the way that they are specified within the map is you put the key first and then the value, and then if you have more than one, you can just keep repeating the key value. So in this case, we have a key of name, and a value of head, and a key of size, and a value of 3. Name here is a Clojure keyword, as is side. All I'll say for now is that keywords in Clojure like this can be invoked against a map. So the purpose of doing that would be to get the value for that key. So we can start a new expression and we can say, here's the keyword name, and if I pass it this map, I want you to return the value for that key. So you can see here it returned a head. And similarly, if we were to do the size, you can see it returned a 3. This is very handy to have at our disposal, and we'll make use of it later. So I think we'll start looking at the data structure itself. We know that given the first problem that we're going to start with a vector, and the one that's given to us here, and it's going to have to go through some kind of process at the end of which is going to produce, well, in this case, another vector. So we know we're going to start with an asymmetrical list, and it's going to have to go through some process, and that will produce a symmetrical list. So we'll just type in here that the process is like it'll symmetrize the asymmetrical list, and it'll produce a symmetrical list. I think from a overall standpoint, this is the task at hand. We're going to take this list and we're just going to produce another one. I think one of the things that we can say is that the initial list is going to have, now we can find this out pretty quickly just using the count operate method function. And we see here that we have 19 elements. And we know that we're not going to have 19 elements when we produce the symmetrical list. It's going to be more because we're going to add a right body part for every left body part. So I think one of the another useful metric would be to say, how many more elements will the final list have? So we want to do a count, but this time we want to filter filter out just the left ones so that we can count them. The filter takes a function, and we're just going to rough in an anonymous function, and it takes a collection. In this case, it's just going to be the asym body parts. Now, the parameter to our anonymous function will be a part, and that part is basically just one of these elements. And now all we want to do is to say, hey, do you start with a, say, does your name start with left? So we can lean on the string starts with, and we can say, hey, that takes a character sequence. In our case, we can now use that keyword to get the value of the name for the part. And then the next thing we want is the substitution, the string we're looking for, the substring. So in our case, it's just a left. And so if we run this, you're going to see we get 12. So I think what we can say here is if we start with 19 and then we run through the symmetrize function, we're going to end up with 19 plus 31, which, it's 31. So that's something we can check a bit later. So within this symmetrize function, I think we got to try to pick out some representative use cases based on the data of the kind of transformations we're going to want to do. And just looking at this data structure, we can see here there's elements that don't require us to actually find a matching right body part. So we can say that's representative. And then the next one is the left one where we do. So if the left, here, let me just move this up here. So if in our case now, if the element is this, well, we just want to produce another one of those. If the element is a left eye, in that case we want to produce a left eye, but I think we also want to produce a right eye. So let's just specify that. And I think those are our two cases we need to work through. Let's just comment that out. Great. All right, so let's start working on the first problem. Okay, so let's focus on building something that will give us these use cases. So let's rough in something we'll call make symmetrical. I'm not sure, let's just go with that. We know it'll take apart, and we know we want it to return either a single part, the same one, or it'll return two parts. So I think maybe let's just try this. We'll start an if, and we'll give it a test, and we'll say, look, if you start with a string, which is like what we have, and we'll take the name apart. And let's just get that in there. If that is true, then we want to return something. We want to return two parts. We want to return the part itself, the one that we matched on left with, and then we want to actually return the right matching part for that. So we can construct a new part here. So we can say curly braces open up to start building a map, and we'll say, look, the first key is this, and it'll be something, and then the size, I think in this case it'll just be the size of the part. So the left and right will have equal sizes. So here we need to do a string substitution. So one of the things we can go to is the replace function, and so we can go in Clojure string and replace, and we can say look at the parameters here, and we have a character sequence S. That's going to be the value of the name key. We'll have to give it some regular expression to match on, and then a replacement. So in this case we'll just say name part again, and then we can do a regular expression by doing the number sign and then double quotes, and we can say if your string that you're matching on starts with, let's say, left dash, then replace that match with right dash. And so that'll give us the true part. Now if the part that we're working on inside of this function doesn't start with left, then we know that it's going to be the other kind of element, which is the head. And in that case, we just want to return the part itself. But I think just to stay uniform in our response, let's put that part in a vector as well. So let's get that over into the REPL, and let's call it on our two examples. See if it's behaving as expected. So we can say if we pass make symmetrical ahead, we expect to get a head back. So what does that give us? It gives us, indeed, we get what we expected there. Now if we try it on the left one, we should get a vector of 2 back. And if we inspect over here, yeah, we get left eye and right eye, and we get size of 1. That's great. So that, I think, will be useful going forward in our solution. How so? Well, now we have a function that we can apply to every element in our list. So I think we're all set up to perform this transformation. We just now need a way to map over this function over these elements. So let's rough in our symmetrize method. That's the one that's going to take asym body parts. And we can say here, let's map. And a map takes a function and a collection. And the way this works is your function has to take as a parameter the element of the list that you're mapping over. So in our case, it's a part. So if I start an anonymous function and say, look, you're just going to be getting a part, and you're going to do something, and then the collection is going to be the argument passed in here, which we gave a name to of asym body parts. So now the question becomes, what are we going to put in for our function? Well, we can just pass it actually make symmetrical. We don't need an anonymous function here. So let me just delete that and just put make symmetrical. So the way that we can read this is when we call symmetrize and pass it an asymmetrical list of body parts, we're going to call map, pass it the make symmetrical, which operates on a single part, and we're going to say, look, apply this to every element on here and give me the result of that. So let's just register this function in the REPL, and let's call it and see what we get. So symmetrize asymmetrical Hobbit body parts, go. Okay, we're close. The form here is slightly different. You can see over here that we just have a vector of maps, and that's what we're going for. But here we have a vector of, or a list of vectors. So what we'll want to do is we'll want to flatten this. And flatten in the sense of we want to take cases where we have two elements in a vector and we want to just make them like a single element. And so Clojure has a convenient method for this called flatten. So what we can do is to say, look, this here represents the output of calling map, and we just want to flatten that output. So what I'm expecting this to give us is we're going to have a final vector that has that's going to look very much like this in its form. It's just going to be a list of these map elements. So let me send the updated method so that when we execute this again, it'll grab it with our changes. And then let's call symmetrize again. Okay, this is promising. We have a list here, and inside the list is our body parts. And what's interesting is it looks like it might be the final symmetrical list, because for every left we see a right. Let me just eyeball these down. It's looking very good. All the way down to left foot and right foot. Okay, so what we don't have it in is a vector, but we might be able to put it into, and you can see here we just have to give it a to and a from sequence. So I think we can say, look, I want to start with an empty vector, and now I want to add the contents of the vector that comes out of mapping make symmetrical over the asym body parts. Let's see if this gives us what we want. Run it again. There we go. I think we can test this out really roughly by just calling count, and we have 31. Okay. All right, well, look, what's interesting about this is that this isn't, it's one way to do this, solve this problem. But not the way found in the book. So let's move on to what the book does. And so the book uses a special form of loop and recur. So the loop recur special form, actually, before we get into that, just rough in a symmetrize, but we'll call it a loop. And we know it wants to take the asym body parts. And then we know that we want to do the loop special form in here. So you can start that off by just saying loop, and you can see here that you get bindings and then the body of the loop. So let's just rough in this spot here, and now we have this started, and we want to determine what bindings we need while the loop operates to produce our final list. So we know definitely that we're going to have the asym body parts as the incoming list, and so let's just call that, name that body parts, and let's bind it to asym body parts, the argument to this function we started. And then we also want, as we work through the loop, iterate to produce a final list. So this will be the symmetrical body parts. This list, when we start the loop, is going to be empty. So we'll bind this symbol to an empty vector. So now that we have our two set up, we can work on the body of the loop. And so let's just, for now, rough in what we want to do, because the loop is a loop recur, and so the last expression in here is we want to call recur. And now what recur basically requires is values for each of the names that we bound in the loop binding. So we need to pass it a body part, body parts, let's say, because this will be body parts. And we need to pass it the symmetrical body parts. And so minimally we could just pass back into the loop whatever we were given at the start of it. So we could just say this. But we couldn't leave it at this, obviously, because, well, for one, we're not performing the make symmetrical transformation, so we'll be never producing the right side of it. The other problem here is that what we'd have is a infinite loop, because recur would just forever pass the same value back into the loop, and we don't have any way of, in our body just yet, to determine when do we stop looping over these values. So one of the things we have to do here then is add some kind of condition. But what is that condition? So to avoid an infinite loop, we're going to have to come up with some test we can do that when it tests true, we can exit out of the loop and have our final list all built within the symmetrical body parts. So the way in Clojure to do this is to, within every iteration, we want to destructure the input list, in our case body parts, and we want to break it out into the first element and the rest of the elements. And so that's and so we want to bind those into some names. And so what we can say here is we can say, look, we want to let, and we want to create some new bindings. And so the bindings we want to do is on the body parts. So to destructure body parts, what we can do is we can start another vector inside, and we can say, I want to call the first element first, and then we'll use an and sign, and then we'll give it another name which just says the rest. And we'll take body parts as what we want to do this on. So the way that you read this is, if you look at our list here, and let's just imagine we had 4 elements in it. And let's say that's what body parts is. When we execute this, what we'll bind the name first to is this first element, which is head. The rest then will become these 3. And so that's just very handy, because now we have the means by which, through every iteration of this loop, we will be passing it in a list that is one smaller than the one that it started that iteration with. So if we continue this example, you'll see that when we execute recur, body parts now will be what I've highlighted here. It'll just be left eye, right eye, and left ear. Well, actually it won't be that, because this is our final loop, but you can imagine up here, right, first will be head, and then the rest will be these 3, and we pass those in, and then we'll take another first and rest, and then left eye becomes first, and then this becomes the rest, and then in the next iteration of the loop, left ear becomes first, and then this becomes the rest. And then on the next iteration of the loop, the mouth becomes first, and rest just becomes nil. I think what we can do is we can test this out. By printing the first here. And we have to put that within an expression where println is the invocable operation. And then we'll call recur, but we don't want to pass it body parts. We want to see how the data is being dynamically shaped as it's going through the loop. So let's pass in rest, and let's just leave symmetrical body parts alone for now. So if we register this in there, now one thing I can tell you is if we run this, because we don't have a check to say, hey, stop calling recur, this as defined, this function is an infinite loop. So if we call symmetrize loop on asym Hobbit body parts, hopefully I'll stop this fast enough so I can show you, but let me execute this and let me get this over the stop REPL. So let me execute it. Oh, and that's an error. What's that about? Don't know how to create. What line are we on? Did I not register that? Let's do this. Let's try this again. Well, one thing I'm doing is I'm referencing REST, but I'm outside the scope of this let. So I think I can grab this and I'll put that there. Let's see if that should at least improve things. Let's get that into the context. Oh, that was fast. Ooh. Hopefully we catch the beginning part of that and we didn't run out of, I think we got it. So you can see here we have 1, 2, 3. Yeah, this is the initial list that we have here. And you can see right away this just would have kept on going forever because REST would have been nil. It would have come back in here. It would have been bound to body parts. And then we would have destructured body parts into a new REST, which would have been nil again. And the first part would have been nil. And so we were just in this infinite loop of nils. So I think what we have to do is we only want to get into this let block and call recur again while we have elements in the destructured REST. So, or in the passed in body parts parameter. So if we now put an if statement in here, we can say if empty, and the collection wants to be body parts. And so if that's true, we just want to return the symmetrical list. So we'll say symmetrical body parts. And then if it's false, just do the let expression, which ends up just destructuring. Here's the print line for our debug purposes. And then we just call the loop again with recur. So let's re-register that. Oh, we'll have to restart this. We lost everything we had in our context, so let's just send over our namespace, get our initial data structure in place, and then let's do that, and then this should stop, and I would expect that the list would be printed, and then that's it. And that's true, and you can see here what we've returned was an empty vector, which is to be expected because we still haven't done anything with our symmetrical body parts. And that's the next thing that we can do. Right now, we have the symmetrical body parts. And this is sort of our accumulator. We want to accumulate the results of doing our transformation at an element level within our incoming list of asymmetrical body parts. And just as we process them, put them into this. So let's just say, look, we'll go into, and we'll say put into the symmetrical body parts list. And what do we want to do there? Well, let's just call our make symmetrical, and we can just pass in the first part. And we know we need to, because we have to start the REPL again, we'll re-register the make symmetrical. And so before we run it, let's just see if we can talk this through. So the first part we're going to pass in is going to be the head, and that's going to return this. We're going to next pass in left eye. Okay, so it's going to work exactly like we expected here. and then this will be a vector being produced, and then we're going to call the into and say, look, take from here and put into this vector. All right, well, let's give that a go, and let's run it. Hey, what do you know? This looks pretty good. Left eye, left ear, right ear, left foot, right foot. Okay, let's do a count. Should see 31, and we do. Interestingly enough, we still have our print line in there, so when we executed the count, it executed that. I don't think we need that anymore. We can just do that. So I think, just to reflect on this a little bit, I think the idea you want to take away from this is that we're basically have two things that are going to be woven within each iteration of this loop. The first one is an incoming list, the one that we called body parts, and given the nature of our problem, it'll be the asymmetrical body parts. And this list is going to be whittled down one element at a time using destructuring. So if you can imagine, something that's 19 elements wide and slowly going down to 18, 17, 16, 15, all the way down to nothing. And then the second part that we're weaving within this loop is the output object, which we've called the symmetrical body parts, to stay true to the domain of our problem. And this starts empty, and it gets wider and wider as we go through the iterations. And it's doing that because this is the operation we're doing on that. We're putting new elements into it based on the business rule of how we make something symmetrical. But this isn't the only way we can solve this. We can also just use straight recursion. So let's look at that next. Straight recursion is very similar to the loop. We're going to have two parts that we're going to be weaving this time. It'll be the same thing. We're going to have an initial list of body parts, and through recursion we're going to still produce our symmetrical list. So let's actually start this off, and we'll call it symmetrize recursion. And unlike the loop, this function is going to have to take the sort of input and output list. So let's just call this let's call this body parts, because we know that's what's coming in, and we know that the symmetrical body parts is what we want also to produce. So with our parameters defined for this function, just like in the loop, we need a way to stop the recursion. Otherwise, it's just going to be infinite. So in this case, it'll just be checking if the body parts is empty. Wow. Had a hard time typing that out. So this is the same idea, right? We're going to start with a list of 19. We're going to call it body parts. It's our input list. And through the recursion, we're going to destructure it so that we can pull out the beginning element in each of the iterations, and those will be smaller and smaller as we just iterate over and over to the point where we know we can break out of the recursion when the body parts list is passed in as empty. So in that case, just like in the loop, we want to return the symmetrical body parts. Otherwise, we want to just call ourselves again. So this is the straight recursive part. There is no loop recur special form. This is just within the function calling itself again. So let's call it, and we'll say recursion. And what we want to do is pass in the rest of the input list. So just like we destructured it down into the first part and the rest of it, I'm going to do the same thing here. In Clojure, we can actually use the function rest, and it just takes a collection. So in our case, it'll be body parts. This will end up leaving the first element. And so executing rest body parts on a list of 19 will return a list of 18. And then the second parameter to our symmetrize recursion is the symmetrical body parts. This is our final list that we want to build. And now we want to perform our transformation on the element, the first element of the list within this iteration, and then we want to pass that in to the second iteration so it can continue building on what we're doing. We'll start with into, and we'll say into the symmetrical body parts. Our good friend, let's make it symmetrical, and now we'll just say give me the first element within body parts. So let's throw that into the REPL, and let's just talk through it. So we have a function, the name we've given it is symmetrize recursion. We've defined two variables, the first one being body parts. That's going to be the list of 19. And the second parameter is the symmetrical body parts. So when we initially call this, we're going to have to pass in what we want to start that off as, and that'll be the empty vector. To avoid the infinite recursion, we'll do our check and we'll say if the body parts in this iteration is empty, we don't want to call, we want to stop the infinite loop. We actually want to get out of this, and let's just return the symmetrical body parts, and let's hope we have been building it in the right way so that it gives us the right answer when the recursion stops. If the list is not empty, the body parts, then let's call ourselves again and pass in the rest of the body parts. So in the first case, if we came in with 19, this will say call us again with 18, and on the first element of the 19 list, transform it by making it symmetrical and place that into our final body parts here. So that talks fine. I don't see anything obviously wrong in that, so let's give it a go. So we'll say, let's start with the asymmetrical body parts, because that'll be bound to body parts, and then we want to say let's start the symmetrical list with empty when we first start. So let's run this. Oh, that's looking good. Left foot, right foot. Let's do our count. should get 31. Hey, that sound looks pretty good. Now there's one more way that we can do this, and that's using the reduce function. So let's do that. The reduce function, you can see here, takes a, you can call it in one of two ways. You can give it a function and a collection, or you can give it a function, an initial value to start off with, and a collection. So in our case, we will be passing it an initial value, and it's going to be the empty vector. The reduce now is very much the same kind of feel as the straight recursion and the loop recur, in that it's going to take an initial list and it's going to perform an operation on it, and it's going to accumulate the result of those operations on each element of the incoming list to produce a final list. So the reduce here, we'll just start off an anonymous function, and we'll say I want to have an accumulated list. So let's just say accumulated. That doesn't look right. Hold on. Well, it is right. That's weird how sometimes words you look at quite a bit just don't look right for some reason. Anyway, let's just keep going. The second argument we want here is the actual part. And so now what is this part? This part will be the element in the incoming list that reduce is going to be moving over. So we do know that the initial value here is going to be an empty list. Now this is going to actually be bound to what we named here accumulated, and actually let's just call this symmetrical body parts. And then the collection itself is just going to be our initial incoming collection. So when you think about this as a loop in a way, you can see here that this function is going to be called for every element of the incoming list, and it's going to take two parameters. One is the sort of output that we want to produce by reducing over the incoming vector. And we want to pull out each element as we do this so that we can operate on it and take the output of that transformation and put it into our symmetrical body parts. So in this case, that'll be considered the body of our method. So in here, we want to do something that should seem familiar to you now. We'll say I want to put into the symmetrical body parts the result of the transformation of the part. So before we run it, let's just talk through it again. You can see a lot of the familiar elements here. We have an incoming list, and we have the sort of list that we'll be producing as we iterate over the elements in the incoming list. And our output list, let's start things off by just giving it an empty list. The transformation we're still calling, and we're still doing it on the part, and you can see here the destructuring and stuff is happening, but we're not really doing it explicitly like we have been doing in symmetrize loop and in symmetrize recursion. Although we didn't technically do it in the straight recursion approach, because we called rest and first explicitly. But you can see here in the reduce, it kind of feels like it's being done behind the scenes within the mechanism of the reduce. It's just saying, look, all you need to give me is the starting list, the initial value of your output list, and a function that takes your output list, so we have a place to accumulate the results of your transformations. Here I'll give you the element as I loop over these things. And now just within the body of this function, make sure you manipulate the symmetrical body parts in this case according to your business logic, which in our case is making the part we're given symmetrical, and we're just collecting it into the symmetrical body parts list. So this isn't in any kind of function. When we run this, we'll get an immediate result. And let's take a look. We got left foot, right foot. That looks good. Head, left. Oh, that looks good. Let's count this. And there we got 31. So we walked, to summarize then, I think we walked through 4 different ways to solve this problem. The first way was not found in the book. This is sort of, you can look at this as like just working through the problem and just taking what's coming to mind and just trying it out and see if it works. In this case, this doesn't use any kind of recursion. We're just running a map on the asym body parts. Once we're flattening those into a vector, and with the make symmetrical function, returning a vector of 2 in the case of left parts and a vector of 1 in the case of all other data scenarios in that list. You can see how short and sweet this solution is, because it's basically this. Now, mind you, the one business rule that we're doing, making a part symmetrical, that solution was put inside this function and is just being reused here. The next 3 sort of share a similar spirit. When you're thinking about these things, you're always going to pick out what your input. Oh, hold on, that's not right. That, although it did look. Okay, let's just fix that. They all start with an input list, and they end with a final list. And within each iteration, as you're working through the initial list and being either you're destructuring out that element to work on, or you're explicitly going in and grabbing the first element within the list that you're working on, or if you're in the reduce case, just rely on the mechanism of reduce to give you that element as the incoming asym Hobbit body parts is being whittled down before you by reduce. You're always going to have those 2. One's going to start empty for the most part in this kind of scenario, and the other one is going to be your incoming list. And they're all the same that way. Now, one interesting thing to call out here in the way that reduce is different than loop recur and straight recursion is that we didn't have an exit or an if check to break an infinite recursion. One of the nice things about reduce is that it will stop on your behalf, let's say, because it is taking upon itself the responsibility of whittling down the incoming list for you until there's no more elements. So I hope you found that interesting. That was the first part of this problem.